Hi guys, so I wanted to show you one more circular motion scenario, and that's this one, the wall of death. So you've probably seen a clip of this somewhere or another. And what it is imagine you have basically a big cylinder, and a performer, somebody on a motorcycle, or sometimes they use like little cars, is riding around the inside of this cylinder. So it's a little tough to visualize, but they're riding around the inside. And of course, you know, this cylinder has some radius r. And it might be actually a little bit easier to visualize this from the side. So if you imagine this is the wall of the cylinder, you know, our motorcycle rider here, we can recognize that the coordinate system that we care about is r and y, and let's put in our forces. So in this case, of course, we would have the force of gravity pointing down, and we're going to have a force of friction that's holding the rider up the wall from falling down the wall. And then it's actually the normal force that is providing the centripetal acceleration. And of course, I'm just going to indicate on here as well that centripetal acceleration is pointed towards the center. And the question that really arises when analyzing this problem is, you know, how fast do you have to go in order for this to work? And we can figure this out using what we know. So I looked up here. The radius on this thing is about 5 meters. And a reasonable coefficient of friction, static friction, for a tire on wood like that is 0.7. So let's see. Let's look at our sum of forces. So if we sum the forces in y, we're going to have the force of friction. It's positive, pointing up. The rider's weight is pointing down. And this is going to equal, in general, this would be the mass times the acceleration in y, but he's not going to be accelerating in y, so this will equal 0. And remember, the force of friction is equal to mu s times the normal force. So we can put this in as well. And this allows us to solve for the normal force in terms of these other quantities. So notice the normal force is going to be mg over mu s. Okay, so let's look at the sum of the forces in R. So in this case, we have the normal force is what's providing the centripetal acceleration. That's going to equal mass times AR. And we know now that AR we can find from v squared over r. And then we can substitute in what we know about the normal force from looking at the y component, or the y direction. So mg over mu s is going to equal m v squared over r. And notice the mass appears on both sides, so that will drop out. And then we can solve this expression, what's left, for v. So if we solve for v, notice we'll have r g over mu s, take a square root. And we can put in our numbers here. This will be 5 meters times 9.8 per second squared over about 0.7. Take a square root. We find that this is about 8.4 meters per second. So this is telling you, how fast the rider would have to go to keep from sliding down the wall. And why don't we just convert this into a number that's maybe more familiar when we're thinking about motorcycles and cars and whatnot. So let's multiply, let's see, put it in miles per hour, how about? Seconds in 1 hour. And when you multiply through, you would find that this is about 18 miles per hour. So it doesn't sound super fast, considering what kind of how the types of speeds that we're familiar with from cars and motorcycles and stuff. It's a little bit difficult to visualize where this is. So remember, this would be tangent to the circle. And in our side view, this would be, pointed at you coming out of the whiteboard. And this is just kind of a neat example, I think, because at first it might appear sort of mysterious, but using what you've learned about centripetal acceleration and how these scenarios work, you can pretty easily explain this in terms of what you know. So, and I'll post a link to a video of this thing in operation so you can see it. It's kind of neat.